Hello there, let's talk about isotopes. So isotopes are going to begin by defining as atoms with the same number of protons and a different number of neutrons. We see in this example here two versions of sodium. Okay, and just in general, I'll define isotopes as being two versions of this, well, multiple versions of the same element, two or more. What sets them apart is not the number of protons. Protons, and that's the same number of protons for a given element. It's the number of neutrons that varies. And we're saying that because our definition of an element is defined by the number of protons. So if you change the number of protons, it becomes a different element. Maybe neon, maybe element 12, which is magnesium. Anything with 11 protons is sodium of some kind. Here we see sodium with 12 neutrons. Here we see sodium with 13 neutrons in the nucleus. So we add these together. 11 plus 12 makes 23, so we're going to call this sodium 23. Here we say 11 plus 13 makes 24, so we're going to call it sodium 24 because there's 24 things in this nucleus, 23 things in this other nucleus. Now, just to be clear about how we represent an isotope, okay, so we have one way of doing it with, the mass the symbol for the element, and then the atomic number would be the number of protons. So if you look on a periodic table, it's generally going to be the one that's a whole number. The mass number is going to be the sum of the protons and neutrons. What you see on the periodic table is you don't see the mass number, you see a number similar to the mass number, but it's an average of the mass numbers of all the different kinds, all the different isotopes of that element that exist. So unlike the numbers on the periodic table, which will generally involve decimals, you're going to put a whole number here and a whole number here because the periodic table shows an average of all the different isotopes. What you're going to write is information for whatever particular isotope you happen to be looking at. The other way to write it is element name and mass number. So examples would be like on this previous one, there's the element symbol right there. So we to make that bigger and more easily visible, sodium with the number of protons and the total number of things in its nucleus. I could also call this sodium 23, and this one would be sodium 24. Now, looking at some other things with this, I suppose there it is once again as an example. I should point out one other little thing. It says electrons equals protons. And whenever you're looking at a neutral atom, electrons, which are negative, will always be equal in number to the protons, which are positive. If you have a neutral atom or a neutral isotope of any kind, this will be equal. When these are unequal, you get a net charge. That's called an ion. That's for another occasion. Now, this right here, this sodium, there's many, many isotopes of many different elements. This is just one example. Here's hydrogen. Hydrogen 1, so-called because the nucleus has one thing in it. Hydrogen 2, because the nucleus has a proton and a neutron. Hydrogen 3, 1 proton, 2 neutrons. Okay, these all have one electron because they're neutral, so one electron to balance the one proton. So remember that the number of protons defines the element, which is why all these things are called hydrogen, because they all have one thing in their one proton in their nucleus. If any of these versions were up to 2 protons, we wouldn't call it hydrogen, we'd call it helium of some kind. Okay, it is not necessary in this class to memorize these particular names, but certainly any student should be able to look at the fact that this hydrogen has one thing in its nucleus and call it hydrogen 1. This hydrogen has 2 things in its nucleus, call it hydrogen 2. And this hydrogen has 3 things in its nucleus and call it hydrogen 3. Let's see. Oh, there we go. Other example, uranium. Looking at this one, you'll see that the number of protons is the same across these different ones because 92 protons is what defines uranium. And then the number of neutrons can vary, and if we're looking at a neutral atom that doesn't have a charge, they're all going to have the same number of electrons compared to protons. Now, what this is actually kind of showing why, if you look at the periodic table for uranium, it doesn't give a whole number. Yes, it's element number 92, but the number it gives is 238 point something or other. There's some decimals that come after that. Reason why? The vast majority of natural uranium is uranium-238. with 92 protons, 146 neutrons. But a small percentage is uranium-235, and a smaller percentage uranium-234. And there's other, this isn't a complete list, there's other isotopes, many other uranium isotopes out there. If you take these numbers and like 99.274% of that number plus 0.720% of that number plus whatever else is the other elements that there, the other versions of the element that there are, you're going to come up with a weighted average that comes out to like 238 point something or other. Now, uranium isotopes, like any other isotope, is going to have very similar chemical reactivity. If it reacts with one element or another, you can generally say the same for all the different isotopes, but they may not behave the same when it comes to radioactive stuff. And so there's actually different kinds of uranium are used for different things, with the uranium-238 being similar to like cadmium or other heavy metals in that you really wouldn't want to touch it or spend too much time around it, but at least it won't set off a bomb. Uranium-235 is what's used in nuclear weapons, either as a first stage primer or actually as the entire weapon. So that's like the diagram for the one dropped on Hiroshima right there, because it is capable of splitting its atoms and releasing a lot of energy, whereas uranium-238 atoms cannot be split in the same sort of a way. So these are some practice problems to try out. Okay, make sure, I would say pause the video before the answers are put up. But here's what you should be able to do. You should be able to come up with the number of protons, neutrons, and electrons for for these two. And this one, you should be able to take this information and come up with a symbol, and I suppose the name too, for that matter. Which, by the way, I'll put up the answers just for the sake of you having something to reference. So I would say this has 80 protons. I'm going to use this abbreviation for proton. And then 201 minus 80 is 121 neutrons. Okay, just to make it clear, that's proton. This is neutron. And if I'm going to do electrons, we're going to assume a neutral atom, so 80 electrons, just because of the fact that if it's neutral, it's going to be the same number of protons and electrons. For carbon-14, I'm going to say 6 protons, because all carbons have 6 protons, and 8 neutrons, and 6 electrons. So you give the symbol for an element that has 15 protons and 17 neutrons. So I look over at the periodic table and I see that element number 15 is phosphorus. P for phosphorus. And it's got 17 neutrons. So first of all, I'm going to put a 15 down here because all phosphoruses have 15 protons. And so that number of protons is what goes down in that bottom left corner. The top left is the total number of things. 15 plus 17 is 32. So I know I just asked for the symbol, but if you were to be asked for the name, I would call this phosphorus 32. Phosphorus 32. Now, I suppose this comes back to what I was mentioning earlier. I'll get all this out of the way. This is the reason why, when you look at the periodic table, you see numbers that aren't whole numbers in there. It's because most elements, there are different isotopes, there's different forms, and so they do a weighted average. 98.89% of that number plus 1.1% of that number plus whatever percent of that number, you average it all out, comes out to an uneven number like that. Okay.